Hello and welcome back to this course on fundamentals of data science. In last few lectures, we have been dealing with some basics for probability and statistics, and today we are going to extend this topic into the topics of regression. So that's in for today. We are going to discuss about some basics for regression, and we are going to highlight what a linear regression is. We will see some examples of linear regressions, and moreover we are going to look at how we can predict things using the regression model. In fact, regression model is one of the machine learning methods. So that is going to be our objective. We know that linear regression is one of the machine learning model, and it can also be used for various data analysis process, including predictions. And to evaluate this linear regression, we use many different methods. We'll start by examining what is ordinary least square method. Well, all is set for us today with regards to linear regression. Let's go and define what is a linear regression. Yes, the linear regression is a statistical model, and this basically uses or helps us to estimate the relationship between a dependent variable, often we call as outcome variable, and one or more independent variable, often we call as predictor or covariance or features. As regression analysis is primarily used for two conceptual distinct processes. First, regression analysis is widely used for prediction and forecasting. It does fairly well for prediction and forecasting, whereas it uses a substantial overlap with the field of machine learning. Second, in some situations, regression analysis can be used to infer a causal relationship between the independent and dependent variables. We are going to see with few examples how it is done. So this is the basic simple linear regression equation, where y equals beta naught plus beta 1 times x plus the error term. So y we call it as the dependent variable, and beta naught is your y intercept. When you have this regression line, y is going to be your y intercept, which is a constant value. Then beta 1 is your coefficient, which we have to calculate in most cases, and x is your independent variable. Maybe now you can relate what is dependent and independent variables. If you look back again, we talked about dependent and independent variables, like so the regression analysis estimates the relationship between dependent variable and the independent variable. Moreover, we also saw that how this relationship can be a causal relationship between these two variables, dependent and independent variables. Again, this approach gives us the basic information about these two variables, dependent variable and one or more independent variables. So this independent variable can be more than one. Yeah, so that's where we feel how this can be extended. You can see here y equals beta naught, which is a constant, or y intercept. Then you have beta 1, beta 2, beta 3. There are a lot of coefficients adding up with a lot of independent variables. That's kind of an extension of multiple linear regression. So often we can see different values that we have here. For example, independent variables are the ones which are observed in data and are often denoted by x. So we have here, that is the independent variable, and the dependent variables which are observed in data are often denoted by y, where we have here, and the error term which is not directly observed in the data are often denoted by epsilon or just E, that is your error term. And the unknown parameter, that can be a scalar or vector. We have here the parameters that we have to estimate. At this point, it is good if you could look at a simple example with the given data. Well, we already talked about what is a covariance, what is the relationship between a correlation, as well as we talked about a few things related to basic statistics. This all started with a table of data. Likewise, here again we have a table of data in which we have to see the travel cost data. So look at this, we have the total miles in X and the total payment of gas in Y, which is Y is the dependent variable and X is an independent variable. So for number of miles you drive, it gives you the amount you pay for gas. So you have this list, but we have to find if the driver, or if we drive for 630 miles, how much shall we pay for the gas? That's going to be your question right now. We have to find it. You don't have for 630 miles, you just have for other values. In some sense, you are trying to predict what is the expected payment for gas you are going to pay for 630 miles. So here is what we are going to use. We are going to use this formula, y equals b naught plus b1x. Generally, in the past we saw it as beta naught plus beta 1, or in short we say b naught plus b1 times x, where beta naught is your y-intercept or constant, and b1 or beta 1 is the regression coefficient or the slope of the line. So since we have this whole data is given to us, we can find the regression equation, which is nothing but this one here, y equals b naught beta naught plus b1 times x. And for beta 1 or b1, we have this formula which we can use to solve it. We don't have time for deriving the formula, so I am not going to derive the formula. Rather, we are going to use this formula to calculate the b1 or beta 1. So data are given to us. What we need is we need to find these terms, like summation of x times y minus summation of x, summation of y by n divided by summation of x square minus summation of x the whole power 2 by n. That is for b1. So you are calculating these values from the table, from the given data, and you are coming up with b1 equals 0.072. Well, with this information, you can calculate what is beta naught, because you know the equation y equals beta naught plus beta 1 times x. So now is that you have finished calculating this, you can see what happens to y with respect to x. Whenever you change a one value, you will see the effect on the other one. For example, here is our regression equation, y equals 8.05 plus 0.072 times x. So if you want to calculate a particular value for y, which is the payment of gas in this case, you just have to plug in the values for x. So in our case, in the previous model or this problem here, what we have, we asked about the question here. The question is, if you drive 30 miles, what would be the gas payment? So accordingly, you can try it out here. For finding y, you can check 8.05 plus 0.072 times 630. You can check that out. This is a simple form of predicting the values. Well, this is what we have for the regression. So with this thought, let's move ahead and discuss more about how this regression is handled. And there are different types of regression as well. The regression, you can estimate the relationship between variables, basically that's the idea behind the regression. And regression, you have different types like linear regression, logistic regression, the basic types. And we will also consider a few more points about what are the other types of regression. There are still a lot of types of regression, including liaison regression and so on and so forth. Well, the scope of this lecture is just with respect to simple linear regression. So linear regression has simple linear regression, multiple linear regression, simple logistic regressions, and multiple logistics regressions. Again, I want to emphasize what this statistical measure is. This, as far as the statistical researchers are concerned, the linear relationship to predict the average numerical value of y for a given x using a straight line, we call it as regression. So let's look into this part again. So whenever we have this form in which you have x and y, and you do have various data points. So these are the data given to you, and then we are trying to predict an average numerical value of y for a given x using a straight line. We call it as a regression line. So we have a straight line, we call it as a regression line, and if you know the slope and the y-intercept, because when I say y-intercept, at some point this is going to intercept with the y, so this point is called the y-intercept. Okay. So if you know the slope at which the line is drawn, if you know the slope and the y-intercept, so we also talked about the y-intercept here in this case, as you can see, the beta naught. This is the y-intercept here, right there. Yeah, once we know this for the regression line, then you can plug in a value for x and predict an average value for y. That's what we saw in the previous example. Once you know the regression equation, you can always predict the value for y, the dependent variable you can predict, just by plugging in the values for x. So that is the basic idea behind this. But there is something that we should be careful when we cannot go for such regression models. So we don't have to do the regression analysis unless we already have found at least some moderately strong correlation between these two variables. There should be some correlation between the two variables. So if the correlation is less than 0.5, for example, then usually that kind of data are not useful for regression models. Generally speaking, those related things, like in this case they do have some relationship, all the data, we can come up with a regression line that can represent such data. But if there is no correlation, it's very hard for us to understand the whole data flow as well as to predict things from each end. Again, here we have the regression line. Let's look at this equation in detail. Okay, this is what we have here. That's our regression, basic regression line equation. And here we can see the salary, which is in the y-axis, equals beta naught plus beta 1 times the experience. Experience is in the x-axis. So experience is your independent variable, and salary is our dependent variable. So just imagine this whole process. If beta naught is 0, then which means that there is no experience, right? But still, with no experience, you can still earn some salary if you get your first job. In this case, that's where your y-intercept is. So you're starting at that point with no experience. You get that beta naught plus beta 1. When the experience that x is 0, you are starting out with some values. But when in some cases we do find that your regression line might start with the origin, right? Sometimes it starts with from the origin, but in some cases we do start from certain point. So in that case, when it starts from origin, we know the value is going to be 0. Well, let's look at this again. We do have many data points. With the x-axis, the years of experience, and y-axis is your salary. So for any given experience, we can actually predict what is going to be your salary. For example, like if you want to know what is going to be my salary, if I have 9 years of experience, you can always see like the 9 years of experience, you got the 2 data points here. Probably this is 9 years and this is maybe 9.3 or 4 years. So basically we do have some relationship coming up at this point of time. So with this we can also see there are some things we can try to estimate. So estimation and the observed values, that's what we are going to observe right now. So for example, for the year 5, when I am 5 years of experience, what is the observed salary? So this is your observed salary for 5 years. And what is my expected, or in other words, the predicted salary? That is this line that we have drawn. This is your predicted salary. So this is one of the examples. Probably we would also discuss in detail like how this can be done with the observed value as well as the predicted value. We will see in details about what is what in a short time. So before we go into that factor, I just want to give you more information about this particular point. So in the same line of thought, we know that for 5 years, this is your observed value. So for observed values of x, you can extend it and check what is your salary. And the same way for the predicted value, which is in the line, you can always check the salary. But you do find some difference, right? At times the difference are quite huge. Yes, with this difference we can actually observe and analyze few things with regards to the regression equations. The same is true with any point of time or any particular values. If you just want to see what is my salary when I am 7 years old, you can see when you are around 7 years old, your predicted salary is predicted line, the regression line is here. So your predicted salary is at this point around 85K. So that's one of the advantage of linear regression model. That's why it is used in machine learning for predicting various things. And for regression, as far as regression is concerned, in order to reasonably evaluate this regression process, the first evaluation matrix is the ordinary least square. So this method is used to estimate the unknown parameters in a linear regression models. So as far as we know that the two parameters, dependent and independent variables, are the two main parameters for a linear function, and with this thought in mind, we can observe and see how we can find these or predict by means of linear equations that we have. The basic goal is to minimize the difference between the observed response in some arbitrary data set and the response predicted by the linear approximation of the data. Right? So this ordinary least square method is used to estimate the unknown parameter in the linear regression model, and its main goal is to minimize the difference between the observed response and in the arbitrary data set and the response predicted by the linear approximation of data. So that is one of the key factor with respect to this observation. So we want to understand what is an observed response and what is the predicted values. So let us look at this equation again and this figure again. It can give us more information on that methods. Okay, again as we have seen earlier, all these points here, all these data points are the observed values of x or observed values of y for x. So all these are very key for us. For example, this is an observed value, here is an observed value, here is an observed value. These are all the observed values. And what is the predicted value? The predicted values are those which are crossing the line. These are the predicted values. And we have to estimate the actual relationship of this regression methods for the observed value as well as for the predicted value. So we know that everything is with respect to y. Y is the dependent variable. We always want to predict y. In this case, I want to predict my salary for a particular years of experience. So I do have observed values already displayed in the graph, and I want to actually predict some values for y. Well, let us look at some examples again. We already talked about few things. For example, at 5 years of experience, this is my observed value, and for observed value you can actually see what is my y. And for this particular one, we do have a predicted value for y at this point here. They are quite different. The observed value and the predicted values are quite different. But we know that observed values rightly represents actual data that we have in hand. But sometimes in this graph we can see for a certain experience we do not have any observed values. In that case, we have to predict what is the actual things there. In this process, we do have to analyze the entire scheme. So for which we can take this form, we can add up all the errors that we have. This is where the error comes in. We talked about error in the regression equation. Let us talk about this error again. So we want to estimate which is the best fit line. As you can see, there are different lines, right? Here is one line, here is one line, here is one line, here is one line. So we have to find which is the best fit line for the regression form, the simple linear regression. How do we know? How do we estimate? One way to do that is to estimate the difference between the observed value and the predicted value and add up all the differences. If this sum is less, then that particular line is going to be your best fit line. To make it more easier, let me give some more examples on that. So just imagine that you are trying to find or estimate this error for this green line. In that case, you may have to take up, for example, in this case, suppose I start for here, this observed value of x, this observed value for x, and here is the predicted values for x. In fact, observed values are given here. So you do have a value for y for this and a value for y for this, right. So we do have this as y and y bar, say y1 and y bar, and again then you can do for each and every data points. Let us consider this as y2 and y2 bar. This one we can consider as y3 and y3 bar. This one you can take it as y4 and y4 bar. So likewise you can add up for each and every data points this differences, y minus y1, y2 minus y3, y2 minus y2 bar, y3 minus y3 bar. So likewise you can add up all the values, all the differences for each and every data point for one particular line and check its sum. Then do the same thing for another line. You have another line, there are different lines we have drawn here. Try to find which line has the best fit with minimum error, and that is going to be our best model or best line for regression. So today we just talked about some basics with respect to regression, linear regressions. Especially we come to know that this regression model is a primary part of the machine learning model, in which you can predict the actual values of y, which is the dependent variable. You can always predict, if with the given independent variable, you can always predict the dependent variables. We do have given with many observation, we have observation data or observed data are there, but there are some values for which you do not have any data. That is what you are going to predict. And in short, we also talked about what is a ordinary least square method, which can be used for a simple evaluation of the linear regression model. So that is all we had for today, and we are looking forward to discuss about regression methods with respect to how we can evaluate the regression model. Especially we have these two methods, R square and adjusted R square. These are two different popular models that are available, and we do have other related models that can be used for evaluation of the regression. So that is what we have for the next session, and I am looking forward to see you there. Until then, goodbye.